So now let's briefly talk about a stochastic process, and the hope is I'll briefly introduce the common growth theorem and Brownian motion. So a stochastic process in probability or statistics is essentially just a sequence of random variables. So sometimes you do the sequence when you're using discrete time. So when the t is in n, you have a sequence. But oftentimes later on, sometimes you do continuous time, so the xt here, t is in the reals or non-negative reals. So let's just take some example, okay? So suppose you have, let's consider the coin toss, and you can do it countably many times. So let's say omega, this big omega is basically all the head and tail, but you toss it countably many times, you raise it to the power n, okay? So another way of thinking that is basically all the function of little omega from n to the set h or head or tail, where omega n is basically either head or tail. That's your the result of the nth coin toss. Okay, so you put everything together, and that's your sample space. And this space, the probability, the sigma algebra is usually not the whole thing. Okay, so you can't really measure everything. So you usually take the product measure. So you treat it as a product of the single coin toss. Okay, so the sigma algebra is really the product sigma algebra, or another way is I should say it's the product sigma algebra. So you do the product of the power set of the nth coordinate, okay, so the head and tail, and you take their product sigma algebra. Another way of saying the product sigma algebra is basically the set generated by the cylinders, or you can say this is the sigma algebra generated by all those sets where it looks like B1 cross B2 and so on. But after you reach a certain point, you just cross everything. Okay, so it's HT and so on. All right, so basically your omega is you only fix the first n coordinates. You allow them to be inside some BIs, but the rest of them you have no control. Okay, so that's the sigma algebra generated by them. And the probability you have is basically you assign the probability of, say, probability of, you only need to define it on these cylinders and you extend it to the whole thing. So the probability you define on B1 cross B2 and so on cross Bn, and then you cross these HT and so on, is basically just equal to the probability of the first n thing happens. So you can say that's the probability of the coin toss happens in B1, second in B2, and so on. Okay, so then you can say that's the probability of B1 cross up to the probability of Bn. So here the probability, just the single coin toss happens in their corresponding BI. All right, so now you have these kind of infinite coin toss measure space or probability space. Let's talk about the two stochastic process. And the first one is the nth one. We probably see that already. So this xi, if I give you a coin toss infinite many times, the xi is just the ith result. Okay, so it's equals to 1 if the ith one give you a measure of if the ith toss is a head, and 0 if the ith one is the tail. Okay, so that's one way of looking at this. And well, you can probably see that each of these coin toss, because each one of them are on a different set. Okay, so the xi and xj, they are basically doing different coins. So you can also see from the definition from here that these xi are independent. Okay, so they're just independent based on the way we defined independence. You can compute the basically if you do the mu of the x1 up to xn, okay, you can see that's just the product of mu of xi. Okay, I go from 1 to n. The reason is fairly simple. I'm not going to show the calculation. You can just do the calculation yourself. Okay. Well, they're independent. While it is a stochastic process, it's not a very interesting one. So let's look at a slightly more interesting one now. So suppose I count how many I tossed, how many heads I tossed. So this is, let's call them yn. Let's define to be the summation of the first n of these xi's. Okay. Well, then you actually also have a stochastic process. Each of these yn are just finite sum of some measurable functions. So again, it's measurable, but they are not independent. Okay, so they're not independent. Clearly, the value of the idea is the value of the yn plus 1 is going to depend on yn. Okay, so suppose at the nth time you already have 3 heads, then you expect the next one to either have 3 or 4. Well, but if yn is, say, so far you get only 1, then the next one you can either get 1 or 2. Okay, so they're clearly not independent to each other. But the nice thing is their differences are independent, so they do satisfy some nice condition. For example, if you have any t1 less than t2 less than tk, then their difference, these y of t, say t2 minus y of t1, up to y of tk minus y of tk minus 1, they are actually independent. Their increments are independent. Okay, so that's kind of nice thing about that. Okay, we're going to see these kind of one way looking at Brownian motion is you take a limit of these y. Of course, you need to normalize a little bit so that it converges. And that's one way to look at the Brownian motion. I'm not going to go that way. Okay, so I'm actually going to do a slightly different approach. Let me briefly talk about the idea behind this approach. Okay. So the idea is that, well, right now we have these x and y. These are examples of stochastic process that defined quite concretely from certain process. Okay, so you have your probability space, you have a very concrete function, and then you can compute their distribution function. But sometimes the idea is that things may not be that concrete. You may only given these joint distribution function, but you don't know how to measure the space yet. Okay, you don't even know if you have a sample space yet. One example is oftentimes you see math finance or in Brownian motion is the following. So suppose let's just consider the following example. Let's let omega to be all the function. Let's say omega, where it's real. It have defined on r greater than equal to 0 to r. Okay, that's basically the represent the trajectory of your stock price. Okay, so that's the stock price at time t. Well, you can make a real value. So, for example, usually you take the log stock price, so everything is now real, so you don't have to care about stock price negative. You just take the log. Okay, so you want to put some measure on this space. Okay, so you want to put some measure on there. So one way to look at this is that you treat it as basically for each real value, each time point, you put in a real value on that time point. So you can look at it as the product space of the reals. Okay, so here is basically t is inside r greater than equal to 0. So on each timestamp, you put a copy of the real and you kind of glue them together. And that's one way to look at the space. And sigma algebra is basically the product sigma algebra. So the B of this on omega is just the product sigma algebra of their Borel sigma algebra. So T is inside R greater than equal to 0. Okay. So you're going to have some nice measurable space, but you don't have a nice measure yet. Okay. So you want to say how likely is the stock price be in this range given certain information. Okay. So that's kind of the idea. So you don't know how to put a probability. So the goal is to put a probability so put a probability measure on this omega and this sigma algebra. Okay, so that's your goal. And you only, well, how do you put that? Well, you may know certain aspect about the stock. Okay, so for some T1 less than T2 up to some TK, you probably know about their joint distribution. So this is the joint distribution or the joint distribution measure of your stock. So you probably know that. Okay. So the goal is that given these joint distributions, so if I give you some fixed finitely many timestamp, and I tell you, well, I know the stock price, for example, now is given at each of these timestamp, I can measure them using this joint measure. Then can I get, is there a probability P, okay? Is there a probability P on this entire sample space, or the omega, this measurable space, okay? So this is kind of the, you're kind of going in the backwards, okay? So you're kind of going from a given joint distribution, and then you try to find a stochastic process or try to find the probability measure, okay? So you're kind of going backwards instead of, say, in the case of coin toss, you start with certain very well-defined measurable function, and then you do their joint measure. So now we're going in the other way. So this is kind of the idea of the common growth theorem we're going to talk about. So I'm going to talk about the conditions first, and then in the next video, I'll briefly introduce the theorem and its application to Brownian motion. But let's look at two things. So first of all, let's think about what happens to this joint distribution. What kind of property it needs to satisfy. Okay, so one thing is the following. So suppose I give you any time, say t1 up to tk, there's some distinct timestamp. And well, one way you can look at their joint distribution at these timestamp, and they may not be in increasing order, so you may want to permute them. So if you let sigma to be a permutation of your timestamp, or let's say 1 to k, then you can consider mu of t sigma 1 and t sigma k, okay? So you can look at two of these. And you can measure one thing, for example, you can measure one at B1 cross B2 up to BK, okay? So joint distribution is defined on k-dimensional process, okay? So you can measure them on these boxes. And when you permute them, you can also permute these coordinate, these boxes. So the B1, well, got permuted to sigma 1. You look at B1 sigma 1, B sigma 2, and so on. And one thing is kind of trivial is that these two should be the same, okay? These joint distribution shouldn't depend on how you pick your timestamp. You can pick them in increasing order, decreasing order, or any order you like. Their joint distribution shouldn't matter, okay? So that's the first condition, so kind of permutation invariant. And the second condition is even easier to think about. Suppose I pick any, say again, T1 up to TK, they're distinct. And if I want to look at T1 up to TK and I look at these boxes, say I have B1 up to some BM, but then for the rest of them, I have reals, okay? So I cross all the reals, okay? So basically I have M of these Brown sets, but for the rest of them, for these K minus M of them, I just take out the whole thing, okay? Well, you know your probability should evaluate 1 on each of these R's, okay? They're just probability on each R. So ideally, that should give you the, basically this probability only depends on the B1 to Bm, okay? In other words, if you only look at T1 up to Tm, and you evaluate on this box B1 up to Bm, well, they should be the same, okay? So basically saying you can project it down, okay? You can, if you have a few timestamp where the set is the whole set, okay, then you can just ignore those sets and you can pretend their timestamp is just gone. Okay, they shouldn't matter to your probability. They should match the probability where you just take T1 up to Tn. Okay. So if you are given a bunch of these joint distribution based on each of these timestamp, well, if they want to come from a stochastic process, then they have to satisfy these two conditions. Okay, that's kind of obvious. But the idea is, suppose you have such distribution now, you want to find a stochastic process. Okay, you want to build a probability measure on there. In fact, these two are just sufficient. Okay, so let's give a definition. So let's define, let's say, the joint distribution mu of T1 up to Tk. So here T1 up to Tk, they're distinct. In this video, we're just taking, we're only caring about when Tk are real values. Okay, so they're non-negative reals, but technically you can just extend it to arbitrary index set. Okay, so this family, we call it consistent if basically 1 and 2 happens. Okay, so basically I want to show that if you have consistent measures, then you have a unique stochastic process that satisfies this joint distribution.